So we welcome our speaker today, longtime friend and colleague, Guram Bezhanishvili, from New Mexico State University, originally from Tbilisi. And he will present his results with his co-authors on existence of measurable cardinals and modal logic. Guram, welcome. Please begin.
Thank you. It's a pleasure to be here. I see many familiar faces, so hello to everybody. All questions are welcome, so you can stop me right in the middle of it if something is not clear.
Mm-hmm.
As you see at the top of the screen, there are four sections to the talk. The first section I called measurable cardinals. So in the first section, each section will be roughly 15 minutes, give or take. So in the first section, I'll review some things about measurable cardinals that we're gonna need for the talk. I'm not a specialist of measurable cardinals. I actually had to learn all those things, you know, when we started to do this project. And so I'll tell you what I learned about measurable cardinals. Then the second topic I'm more familiar with, topology and modal logic. So I'll give you roughly an idea, a little bit of history, and then how, what exactly our program is in studying these things. And then starting from part 3, we will switch to more towards the main result of this presentation. And then I'll finish with the main result. There are some pictures that one of my co-authors, Joel, made. All the pictures that you see are made by Joel. He's very good at drawing these pictures. And these pictures will give you an idea roughly how this main theorem was proved. And again, so whenever something is unclear, please ask me questions.
Mm-hmm.
So I'm gonna start with pointing out that we're gonna work in ZFC. Couple of basic definitions. By an ultrafilter on a set, I'm gonna mean an ultrafilter in the Boolean algebra of all subsets. And as we all know, it's provable in ZFC that ultrafilters on any set exist. That's basically the Zorn's lemma argument. Now, so what is the connection to this measurability? In fact, every ultrafilter gives rise to what's known as finitely additive measure. Finitely additive means that the measure of finite union of disjoint sets is the sum of these sets. And what basically you do is that you send everything in the ultrafilter to 1 and everything else to 0. And then it's an easy exercise that this indeed is actually two-valued measure. And the basic idea is that you think about the sets in the ultrafilter as large sets of measure 1, and then the sets outside of the ultrafilter as small sets of measure 0. But this is only finitely additive measure. To have a real measure, then what you need is that the function actually commutes with countable unions of disjoint sets. And for that, we need to work with what's known as this countably complete ultrafilters. And of course, these are only interesting when your ultrafilter is free, which means that intersection of all the elements in the ultrafilter is the empty set. And so here comes our first important new definition. And a free ultrafilter is countably complete if it's closed under countable intersections. Means that if you take any countable family of elements in P, and if you intersect that, that stays in the ultrafilter. Now, observe that it's important that this condition only makes sense if you work with large sets of large cardinality. If your set is countable, then you're not going to have a countably complete ultrafilter on it, because you can easily show that intersection of these cofinite sets, countable intersection, is going to be empty, and so it's never going to be on the ultrafilter. So already here we need to work with sets of large cardinality. And then the same idea works here, that now these countably complete ultrafilters give rise to this countably, what's known as countably additive measure, which is the actual measure that people work with, but it's two-valued, of course, again.
Mm-hmm.
And then you generalize this to an arbitrary cardinal kappa, and you say that your ultrafilter, your free ultrafilter is kappa complete if for any family inside the ultrafilter of cardinality strictly less than kappa, the intersection stays in there. And these give rise to what's known as kappa additive measures. And again, they are all going to be two-valued.
Guram, so sorry for interruption. Can you focus your, can you raise up your camera view a little bit so that your face is in the center, if it is possible? That's better. That's better. Mm-hmm. Okay. Yeah, good. Mm-hmm.
Now, so here comes this main definition. We say that a cardinal is measurable if there exists a kappa complete free ultrafilter on it. And we say that it's Ulam measurable if there is a countably complete free ultrafilter on it. These definitions are due to Ulam back in 1930. He was the one who started this direction in set theory. And here are some known facts. The first one is a triviality, because measurable means for any kappa, and then Ulam measurable means for countable, and these kappas are, of course, you know, have bigger cardinality, so it's triviality. But this is a non-trivial result that this goes back to Ulam, actually, who showed that if you can, if there exists an Ulam measurable cardinal, then you can prove that there exists a measurable cardinal, and you can do that in ZFC. Of course, what's known by now is that you cannot prove in ZFC whether these measurable cardinals exist. The book that I used to learn some of these things, this was Jan van Mil who actually told us some of these things, and this is the source that he provided. I highly recommend this book. It's an old book from the 70s by Comfort and Negropontis, and not only for the reasons of measurable cardinals, but in general, it's a very nice book about ultrafilters. Okay, so this is basically, and it only took 10 minutes, so maybe I can use this 5 minutes for the next section. So this is roughly what's needed about measurable cardinals for the rest of the talk. The important thing to point out one more time is that it's not provable in ZFC that these large cardinals exist. So now something that seems to be unrelated. This is the connection between topology and modal logic. And so this goes back to Kuratovsky's work. In the early 20s, this was actually his dissertation, where he gave, this is early 20th century. So the notion of topological space, and then this area of topology is a brand new area. The axiomatization that is now acceptable was first given by Hausdorff in his famous 1914 book. So this is only several years later. In his dissertation, Kuratovsky showed that you can axiomatize topological spaces using this closure operator. And now what happens is that this closure operator, the axioms of closure operator resemble very well this Lewis's modal system S4. And so here on the screen, you know, I have this one-to-one correspondence. And now these suggested this topological semantics of modal logic that goes back to McKinsey and Tarski. There were some other people also involved in early on in these things. We're talking about late 30s, early 40s, but somehow, you know, the history only remembers this fundamental work of McKinsey and Tarski from 1940s. The basic idea is that you interpret modal diamond as closure and modal box as interior. If you want to phrase things in terms of satisfaction, then it's good to recall when a point belongs to the closure. A point belongs to the closure if and only if each neighborhood of the point hits the set. And that's exactly how we're interpreting diamond here. X satisfies diamond if and only if for each neighborhood of X, there is going to be a point which satisfies this phi, because this phi is going to be interpreted exactly as the set whose closure this diamond is going to be. And dually, you get that box is interpreted if and only X satisfies box if and only if there exists a neighborhood which is entirely inside this value of phi. Now, we can introduce this notion of the logic of a topological space. You basically take your topological space and you look at all the formulas which are true under every valuation on the space. These are called valid formulas, and so it's an easy fact to prove that these form a normal modal logic, and it's always an extension of S4 because this closure operator axioms match the Lewis's the axioms of S4. And so I'll call this logic the logic of X. And now
sorry,
here comes
for a second. Just to go back to the semantics itself. So I understand for the Boolean connectives, they're just the Boolean operations on the space.
Yes.
And for atomic formulas, it's just there's a fixed assignment of atomic formulas to each node in the space.
Yeah, so what you do is this, that you can think about it globally, that every formula is interpreted as a subset of your space, but then you can talk locally what it means that a point X satisfies a formula, right? So globally, every formula becomes a subset under a given valuation, becomes a subset of your set. And then either X belongs to that subset or it doesn't. If X belongs to that subset, then we say that X satisfies that formula. And if it doesn't belong, then we say that X doesn't satisfy. So formulas are subsets of your space. And then a point in your space satisfies a formula if it belongs to that subset.
Okay, thank you.
Yeah. And then, so here's the celebrated result of McKinsey and Tarski. Now let me explain some of these words here. Well, I'm adding non-empty here because, you know, if we want to get a consistent logic, we always have to work with non-empty spaces. Now, metrizable means that the topology is coming from a metric, and I don't have on a slide what a metric means. I'm assuming that that's okay. Now, crowded is means that every point is a limit point. For example, the real line is crowded, but say an ordinal is not crowded. And so these crowded spaces are also sometimes called dense in itself. Now, the statement that I put up here, that's really not the original statement of McKinsey and Tarski. In the original statement, they really had this notion, this additional condition that the space needs to be separable. These can be actually dropped. This was proved later by Russell and Sikorsky, but the proof is a rather non-trivial use of the axiom of choice. So it's not trivial to drop the condition, actually. And a little bit more history here. Again, somehow history has its own ways. You know, this theorem in its generality was really proved by Eilenberg, actually. But somehow it's mentioned so, you know, in the work of, in this paper by McKinsey and Tarski. McKinsey and Tarski only had a very special version of the theorem, you know, but somehow, you know, this version is, this McKinsey and Tarski's name is assigned to it. Okay, so this is considered a classical result, and this is considered actually the end of the first phase of the study of topological modal logic. And this is something that I'd like to spend a couple of slides discussing what I call this Tarski's program. This paper in which this main theorem was proved, they termed the paper the algebra of topology. And they had this program of actually studying topology by means of these algebras that they defined there. These algebras are the so-called closure algebras. Modal logicians like to call those algebras sometimes interior algebras, sometimes topological Boolean algebras, sometimes S4 algebras. These are exactly the algebraic models of S4. And so Tarski's idea was that, and remember, this is 1930s, 1940s, so topology is still a brand new branch of mathematics. So they wanted to develop algebraic means to study topology, which is reminiscent to how algebraic geometry was developed, that some geometrical properties were difficult to study by geometric means, and people developed, these rings of rings of polynomials to actually study these geometric phenomena. And that's my understanding, at least my interpretation of what Tarski wanted to do. But at the time, this didn't mean to be, because shortly after Tarski switched to studying these Boolean algebras with operators, closure algebras are particular cases of these, by means of these corresponding relational structures. And then he started to develop this theory of relational algebras. And then that resulted in this famous Johnson-Tarski representation theorem from early 50s, which nowadays is considered as precursor of Kripke semantics. But already starting from middle 50s and the second half of 50s, Tarski switched to the study of modal theory, and basically that became, the main area of his study from the 50s on, and it became one of the main branches of logic, especially in the United States. Now, but there were some important directions that came out of Tarski's program. And in fact, you can think of one direction as the beginning of the modern study of modal logic in its broad sense. And then the other direction that I think also had an important push from Tarski's program is what we nowadays call point-free topology. This is now an independent branch of topology with its internal problematics. And the way that things were developing in the 50s and 60s, and probably all the way to early 2000s, was that these two branches were developing in their separate ways, but there were a lot of connections, and these connections, people started to investigate these connections closely only in the last 20 or 25 years. One thing that on the modal logic side that came out of this Tarski's program is what I call this modal logic of topology. And the way that you can think about it is that on the one hand, you can think of modal logic as a convenient invariant to study topological spaces. You say that two topological spaces are not distinguishable if they have the same modal logic. And so you can study topological spaces from that point of view. This is a more, it's a different invariant than just homeomorphism, right? Because you can have two non-homeomorphic spaces that give rise to the same logic, as follows from the McKinsey-Tarski theorem. And on the other hand, you can look at topology as a vehicle to study logic whenever you prove some interesting completeness result with respect to some well-studied topological space that actually uncovers some properties about the logic itself. So for example, S4 is the logic of the real line. So that tells you some things about S4. So some of the things that people started to do lately is to try to obtain these classification results. One of the things that we were able to do was to actually classify modal logics of metric spaces. So for each metric space, you can determine what its logic is. And so that builds on this McKinsey-Tarski theorem. But more generally, metric spaces are very special spaces. And so good ones and very important ones, especially in the study of analysis. But still, topologists consider other spaces, larger classes of spaces. One important class that topologists work with a lot is that of compact Hausdorff spaces. And so there are still open problems for compact Hausdorff spaces. We don't have a full classification of the logics that come from compact Hausdorff spaces, even if you restrict to the special subclass of scattered spaces. These are the ones where, these are very special ones, and they came about from Cantor's study of the derivative. And the good examples of the scattered spaces are actually ordinals with their interval topology. And while we can tell what the logic of a given ordinal is, there are some weird compact Hausdorff scattered spaces that actually can rise to very strange logics. And the combinatorics behind these difficult spaces can be rather complicated. And so I'm not very optimistic that it's going to be easy to classify all these logics, because already just for scattered spaces, you know, that's at least what my intuition tells after working with these guys for some time. Now, even more important class, for probably the largest, best studied class of topological spaces is the so-called Tikhonov spaces or completely regular spaces, depending on which part of the world you live and which topological school affected that part of the world most. You call this either completely regular spaces or Tikhonov spaces. So in the US, they are usually called completely regular spaces, but in Europe, they are usually called Tikhonov spaces. And of course, the name Tikhonov is attached to them because it was Tikhonov who characterized them. And up to homeomorphisms, these are exactly subspaces of compact Hausdorff spaces. So already for compact Hausdorff spaces, we don't have a full classification. Now you're looking at a much larger class. And so this is a good class to try to obtain some results about. And so this program, you know, that my co-authors and I call is exactly, you know, to try to classify the logics arising as LX for some Tikhonov space X. Now, some things that you can do that came out of this approach, I'll mention them, but not in detail. But it shows you a very fruitful interaction between topology on the one hand and modal logic on the other hand. So for example, on the topology side, we were able, our study delivered this new notion of dimension. Remember that dimension theory was one of the better studied directions in topology back in the 40s, 50s, and 60s, starting from the 20s actually. And there are several dimension functions. And so, in fact, we called it modal crude dimension because on the one hand, it's related to crude dimension in algebra. On the other hand, it's a new dimension function on topological spaces. And yet it's very closely related also to modal logic because it basically measures the depth of your logic. On the logic side, one of the classifications, recent classifications, is that of this new class of what we call Zeemanian logics. Back in, I think it was in 1973, when Zeeman introduced this, his logic in his book. Zeeman was a philosopher who was interested in modal logic. And so this logic was characterized by Segerberg back in the 70s. And it played a prominent role in the considerations in the 70s. So it turns out that it also has a very interesting topological meaning. And I'll mention what its topological meaning is in a little bit. But then this Zeeman logic actually generalizes and gives rise to the entire family of what we call the Zeemanian logics. And so they are very closely linked to an important topological property that I'll discuss in a little bit. Okay, so now I'm switching to part 3. So I'm slightly ahead of the schedule, which is a good thing because I can use some time later. So now here's this new notion. Here's a new class of spaces that I want to concentrate on. These are the so-called extremely disconnected spaces. These were first introduced and studied by Stone back in the 30s when he was developing his duality theory for Boolean algebras. He wanted a condition to characterize complete Boolean algebras, and that's exactly what that condition is. I was convinced for a long time that this name is due to him, but as it turned out, the name is actually due to Hewitt, who was his student. He got his PhD from Stone, but then he wrote several very important papers in topology, but then he switched to analysis. And you probably heard, I mean, if you're familiar with harmonic analysis, the most famous book in harmonic analysis, called The Abstract Harmonic Analysis, has as one of the authors Hewitt, and it is exactly that Hewitt of the Hewitt and Ross fame. So he is the one who first introduced this name, extremely disconnected. And what does it mean? It means that the closure of each open set is open. Now, more in terms of the closure and interior operator, it basically tells you that the closure of interior is contained in the interior of the closure. And that immediately tells you that these are exactly the models of S42. S42 is one of the famous extensions of S4 by this axiom, which in Kripke semantics tells you that this Church-Russell property is going to be satisfied. I'll mention that in a minute in more detail. Now, this fact probably was, as far as I know, it's the first time that it was in print is in David's master's thesis. People probably knew that before, but I'm not aware of any printed discussion of this until Gabelaya's master's thesis back in 2001. Now, as soon as you start talking about extremal disconnectedness, one of the most important topological spaces, non-metrizable, pops up, and that's the Stone-Check compactification of natural numbers. So you put discrete topology on natural numbers, and then what you do basically, you take the power set, and then you take the Stone space of the power set. So that's your Stone-Check compactification. And that's how actually now modal logic starts to enter, you know, this weird world of large cardinal axioms. Because many things about beta omega you cannot prove without using either continuum hypothesis or some other additional set theoretic axioms that are not provable in ZFC. And there are many interesting books or chapters on beta omega. If you're interested in these statements that require these additional axioms, I would highly recommend Van Meel's chapter for the Handbook of Set Theoretic Topology, which is called An Introduction to Beta Omega. So here was our first, I would say this was the first time that I encountered something in my research that was beyond ZFC. So this Stone-Check, I mean, think of what Tarski did as taking a very prominent space like the real line and determining its modal logic. So now, what is a prominent non-metrizable space that, well, there's many of them, but one of them you could think of as this beta omega, right? And so determining what the logic of this beta omega is actually took something outside of ZFC, because what we needed to do was that we needed to work with large anti-chains in the power set of omega, and we needed to control the cardinality of these large anti-chains. And so this additional axiom that we used says that all these anti-chains have cardinality that of continuum, and based on that we were able to do some things to obtain finite configurations as interior images. So it stayed, and now this is more than a decade ago, and so people tried hard to actually drop this additional condition, and some simplifications were obtained, but it wasn't until very recently that Alan Dow actually used this infinite combinatorics, very heavy duty technique from infinite combinatorics, to actually show that you can drop that condition and you can prove this. result in ZFC. So this, while I was not convinced that this was possible, it turns out that you can determine the logic of beta omega within ZFC. But what I'm going to talk about in a little bit will require something outside of ZFC.
Could you perhaps tell what kind of techniques, combinatorial set theoretic techniques, was used here for this result of L and Dow?
This is very recent, Lev. I haven't fully digested the proof yet. I mean, this is just several months ago, you know. So I can point you towards his, and the paper is not even published yet, but he has some kind of draft of what he has on his webpage, and I can direct you to that. But it's, I think it's best that I don't say more because I don't fully understand yet exactly what was the critical part of it.
Okay.
But it's a very non-trivial combinatorics that he's using there. So this is certainly something that I have on my list of to-do things to really understand fully how he managed that, because I still don't understand fully, you know, the key, what was the key move. But it was this infinitary combinatorics, some advanced Ramsey theory type of things that he used.
Okay.
Now, so that this is the Church-Rosser property that I mentioned earlier. So if you look at this S42 from the point of view of, well, first, you know, let's connect Kripke frames to topological spaces. This is the standard fact that I'll mention briefly, that Kripke frames for S4, these are reflexive and transitive relations on a set. And you can make this always into a topological space by defining the closure operator to be R inverse. These are called Alexandrov spaces because Alexander was the first who studied these back in 1930s. And now for S42, what you need to satisfy the S42 axiom is this Church-Rosser property, which basically tells you that if you fork, then you have to come back together. And that's exactly what S42 tells you from the point of view of Kripke semantics. And I also want to mention a stronger condition, that of linearity, because Church-Rosser tells you that if you fork, then you come together. Linearity doesn't even allow forking. And so you can prove, these are known facts from maybe the late 60s, 70s. Then you can, 70s, I would say, then you can define this system that is denoted by S4.3. And this S4.3 is an extension of S42. And it basically tells you that this linearity axiom is satisfied if and only if this additional condition holds, that you cannot fork at all. What's interesting, especially from the point of view of topological semantics, is that this linearity is nothing else but Church-Rosser, but not only on the entire set, but requests Church-Rosser to hold on any subset. If you request that Church-Rosser holds for any subset, then what you get is exactly linearity. And so in a way, you can think of S43 frames as those S42 frames, or as those frames that are not just S42, but every subframe is also S42. And so that gives you an idea how the topological condition needs to be changed now. And this is the topological condition that we call the hereditary condition. Extremal disconnectedness tells you that the closure of each open has to be open. Now request that not for all subsets, but also subsets of any subspace. And that's this hereditary extremal disconnectedness. And these now turn out to be exactly the models of S43. And now what I want to do, I want to look at good HED, good hereditary extremely disconnected spaces, those that are also Tikhonov, because that's what topologists looked at. They are not going to look at non-Tikhonov spaces. And so let's call this HED spaces. And now these turn out to be exactly the spaces that give rise to these Riemannian logics. And being a Riemannian logic in this case simply means that, remember, being linear means that you are a chain, but each point can be a cluster. So you have a chain of clusters. That's what being S43 means. And now, in order to be Riemannian, what you need to request is that in the bottom, in the root cluster should have only one point. So the root cluster should not be a cluster, it should be just one point. That's exactly what Riemannian means. And that's exactly what these hereditarily extremely HED spaces give rise to. Now, what that tells you is that there's a complete classification of logics that arise from HED spaces. So we can handle HED or logics above S4. We can determine exactly which logics above S43 are logics of Tikhonov spaces. So then, so what that tells you is that on the one hand, you have this nice classification for modal logics arising from metric spaces. And here's another classification on the other side of the spectrum, that you have complete classification of these H logics that come from HED Tikhonov spaces. So a natural generalization of this would be to try to work not just with S43, but to work with S42. And that's considerably more complicated, and that's where these additional set theoretic assumptions start to lurk. And that's what I want to talk about next. So here's the main result. So we're now going to the last part of the talk. So we're going to talk about the main result. Now, if you think about the simplest Kripke frame, that is S42 still, but is not S43. So you should allow forking, because you should not be linear. So a forking needs to be allowed, but then the forking should come together. So I think that you all agree that the simplest such frame is what's on the screen. So let's denote the logic of that by L. And already the simplest counterexample to S43 gives you this something that I did not expect at all. And what it gives you is this, that in order for this logic of this simple configuration to be complete with respect to a normal space, and observe how I'm switching on you from Tikhonov to normal now. Tikhonov spaces, the class of Tikhonov spaces is bigger than the class of normal spaces. Normal spaces are stronger. The condition of normality is stronger than being just, Tikhonov means completely regular. Normality means that, completely regular means that you can separate a point from a closed set. And normality by a continuous function into 0, 1. Normality tells you that you should be able to separate two closed sets by such a function. So I'm switching from Tikhonov to normal because I cannot prove this. We cannot prove this theorem for Tikhonov. But as soon as you strengthen Tikhonov to normal, then this simple configuration gives you topological completeness if and only if these measurable cardinals exist. And so what I want to do for the rest of today is to give you an idea how this can be done. And so there are two directions we need to prove. First, if measurable cardinal exists, then we need to build the space that I'm calling Z here, whose logic is going to be the logic of that simple configuration. So let's see what we need to do here. So start with this ordinal kappa, which is measurable. Since it's measurable, it has this ultrafilter. And now I can take a space which consists of this kappa together with this ultrafilter. And down here is this picture that Joel drew. So all these points above are the Kappa points, they are isolated points. And this point down, which is the P point, this is the new point that we added now. This is a limit point. And we need to determine what are the neighborhoods, open neighborhoods of this point. And we say that U is an open neighborhood of this point if and only if you take this point away from U, then this difference is going to be a subset of your Kappa. And either that subset belongs to Kappa, belongs to this ultrafilter P, or it doesn't. So if it belongs to the ultrafilter, then this U is going to be your neighborhood. And if it doesn't belong, it's not going to be its neighborhood. Observe that this is not a compact space. And then what you do now is that take two copies of this thing and now identify them. So you get this picture. And now the first thing that you prove is that this space is a normal space. And what's even more important, that it's a P space. Now, P space means that these G delta sets, G delta sets are countable intersections of open sets. So they need to be open. And that's exactly where this ultrafilter, being a Kappa complete ultrafilter, is going to matter, because it's going to be closed under countable intersections. And that'll allow you to prove that your space is actually countably complete. I mean, that your space is P space. So that's one step. Now comes what I call these heavy duty embedding theorems. There's a whole bunch of them that we need to use. So there are three embedding theorems that we really use here. The first embedding theorem tells you that this new space that you built, you can embed into, this is the Dow-Van Mill theorem from the 80s, that each normal P space you can embed into a compact Hausdorff extremely disconnected space. So this Y will be embedded into compact Hausdorff extremely disconnected space. Then there's this famous theorem of Efimov that goes back to 1970s. Efimov was a famous Russian topologist. Then he proved that every compact Hausdorff extremely disconnected space you can actually embed into beta of some cardinal mu. And then as soon as you have beta of some cardinal, then that you can embed into its remainder. And so what I have pictured here, the red dots on top, that's your mu. And then this blue rectangle, that's the remainder. And the basic idea is that this space, this Y space that we started with, which we proved that is a normal P space, you can embed into this remainder. And now you take, now here comes the key, that you take out. So now we have now I'm ready to define what my Z is. Z will take all the isolated points from mu and then the entire Y. But now you take the Z as a subspace of beta. So let's go back. So this is your beta mu. Y sits in the remainder, and then the isolated points of mu are on top. And now you take this entire space mu together with Y as a subspace of beta mu, and that becomes your Z. So in terms of the derivative operator, you can control this space pretty well, because what does the derivative operator do? The first application of derivative will throw away all the mu points, because these are your isolated points. The second application will throw all the isolated points in Y. And then the third application will throw this limit point, which is your free ultrafilter P, away. So really, in terms of Cantor-Bendixson rank, you're applying Cantor-Bendixson derivative only 3 times. So you're a scattered space here. Of Cantor-Bendixson rank, just 3. And you should be, because you need to get your diamond, because the logic of the Z should exactly be the logic of the diamond. So it cannot have Cantor-Bendixson rank any more than the Cantor-Bendixson rank of the diamond, and the Cantor-Bendixson rank of the diamond is 3. So now this is how you define your interior map onto your diamond. So the top part that is colored into blue, all these colorings are done by Joel, by the way. I'm not that good with drawing in LaTeX. So all these blue dots go to the top, the red ones, oops, what did I do? The red ones go to the red dot, the green ones to the green dot, and then the purple one to the purple dot. And now what you do is that you check that this is indeed an interior map. This is not difficult to check, but that gives you one inclusion. That tells you that, and by interior map, I mean a map which is both continuous and open. These are exactly topological analogs of p-morphisms in the world of Kripke frames. And so that gives you one direction. Since this diamond is an interior image of Z, the logic of Z is contained in the logic of the diamond. And now comes the hard direction. Now you need to prove that the logic of the diamond is contained in the logic of Z. The way you can do it is using semantics. All you need to show is that whatever is an interior image of diamond is going to be an interior image of D. Is going to be an interior, whatever is an interior, excuse me, whatever is an interior image of Z is going to be an interior image or a p-morphic image of diamond. So if you show that, then you know that the only Kripke frames that arise from Z are exactly the Kripke frames that arise from D. And hence, they have the same logic. And this is a harder part, so I don't have time to explain exactly the details, but basically what you need to do is that you need to look at all the Kripke frames of depth 1, rooted ones. Well, there's only one such thing, so no problem. Then you have to look at all the Kripke frames of depth 2, rooted ones, that are S42 frames. There's only one such, which is the 2-element chain. So that's also an easy case. And finally, you have to look at the Kripke frames of depth 3 that happen to be, and by the way, no clusters also. Clusters are not allowed because our logic is the logic of a scattered space. We showed that this space is a scattered space, so no clusters. So you're really working with partially ordered sets, rooted partially ordered sets of depth 3 that happen to satisfy Church-Russell. And so the only interesting case is if you're depth 3 and your root forks into many spots and then comes together. And we need to show that these things are not allowed. And that's the hardest part of this direction of the proof, to show that if you fork many times, you can only fork twice. If you fork 3 times, then you cannot be an interior image of Z. So that's the combinatorial thing that we need to prove in order to be able to finish this direction of the proof. And remember earlier I mentioned that there's a lot of combinatorics that comes into play, and that's why as soon as your configuration becomes more complicated, then some of the combinatorial things could become almost impossible to overcome. Anyway, so that's how measurable cardinal gives you this space Z. But observe that the part where we used that the cardinal was measurable was in proving that the space we constructed was a p-space and normal p-space, and then being normal. So if somebody tells me, give me in 2 words, describe what are the key moves. The key moves are the following: that measurable cardinal tells you that the space you built is a normal p-space, and then you use these famous embedding theorems of these normal p-spaces into beta mu for some large cardinal, and then the rest is just relatively straightforward technique. So the key part of where measurable cardinal is used is that you build your space, which is a normal p-space. So in the other direction, again, we're going to use I'll describe what are the key moves, and then let me see time-wise. So I have 10 minutes before my 1 hour is out, right? I think. Okay, so other direction. Now suppose you have a normal space whose logic is exactly this configuration. The first thing you prove is that that means that you have an interior map from your space into your finite configuration. And the way this interior map works is that the space Z gets broken into 4 pieces. Piece A goes to the root. Piece B0 goes to the left forking. Piece B1 goes to the right forking, and then the C piece goes to the top. So these are the 4. This is how your space is broken. And now there are some reduction theorems you need to do. The first reduction theorem is that you can assume that this A actually is a singleton. So there's a little bit of proof involved here, but I'll skip it. Mm-hmm. The next thing, and this is the key part, right? So now, if this is your singleton, then what's going to happen now is that this point A is going to become a P point. Remember, this being a P space is a very critical thing, because that's where these countable intersections of open sets stay open. And so without loss of generality, you can assume that this A is a P point of B0 or else B1, whichever you like. But it's really this move where we can only handle this if our space is normal. If the space is not normal, then this move is impossible. And then after that, what you do is that you take that B0 and you partition this B0 into pieces. And then that allows you to define an ultrafilter on this partition space. And then the fact that this point was a P point allows you to prove that this ultrafilter is countably complete. And remember, that's why I mentioned early on, not just measurability, but also Ulam measurability, because we're not really proving that a measurable cardinal exists. All we're going to prove is that Ulam measurable cardinal exists, and then apply Ulam's theorem that tells you that if Ulam measurable cardinal exists, then a measurable cardinal exists. So we can only handle countable intersections because we can only work with these P points, and P points only carry information about countable intersections. And so that's the end of it. So after you prove that it's Ulam measurable, then you refer to Ulam's theorem, which says that hence, since Ulam measurable cardinal exists, then within ZFC you can prove that a measurable cardinal exists. And that's the end of the proof. And like I pointed out, normality was critical. So the following question still remains open. It's unclear whether we can replace normal by Tikhonov. And the technique that we developed, if you want to do it for Tikhonov, then you have to develop a different technique, I think, because our technique does not allow to do this for Tikhonov. So it still remains an open problem whether completeness of that diamond with respect to a Tikhonov space is provable within ZFC. And more generally, it seems like there's this very close connection between existence of large cardinal axioms and some sort of topological completeness with respect to some different classes of normal, or maybe even smaller classes of spaces. And I think that it's a worthwhile direction to understand better connections between the existence of this large cardinals and topological completeness above S42. And I'm emphasizing that it's important that you stay above S42 because that's when you're extremely disconnected, and these ED spaces are the ones that have close links to this higher axioms of set theory that are not provable in Zermelo-Fraenkel set theory. And I think that that's all that I have to tell you.
Okay, yeah. Very interesting. Thank you very much. I have some questions. Maybe I ask my question first, and then the other participants will ask their questions. So, if you go back to this construction that you presented, so will anything change if instead of the logic of interior or closure, you consider this
Oh, the derivative?
Derivative, yes. So it seems that somehow this is also a scattered space, right? So in a sense,
I think the only thing that yeah, because if you're scattered, what that means is that this interior map has to be more. The inverse image of each point has to be what is this called? What do we call this? Remember that when you have these interior maps, there's these two conditions that you have to satisfy.
yeah.
If you have
So there is this notion of D map, which preserves.
D-map,
So,
yeah, D map. And
so my impression was that your the construction of the previous slide, where you have this, where you
see, the problem is that the problem could be in so in the previous direction, for example, when you build this map, let me go. So this
exactly,
right?
Yes, that one.
Yeah, I think that this should be okay because the inverse image of each of these points is going to be, this direction will be okay. This direction will be okay. And then in the other,
you just need to take diamond irreflexive.
Yeah. Huh? Yeah, diamond irreflexive. Yeah, all points are irreflexive here. Yeah. I need to check some of the details, but my guess is that this may actually work also in the D-semantics.
Yeah.
So let me write this down and then check it. Yeah, the only additional thing that we have to be careful about is whether or not this DMAP condition is satisfied. And it on the surface, it looks like it is satisfied, at least here. But I think that there are several reductions that we're doing. And so I need to make sure that all these reductions allow you to switch from interior map to DMAP. So I'll check that and report back on that.
Yeah. Okay, we have some. Okay, thank you very much. On my side, I see some some disturbances in the sound, but not really that bad, so one can distinguish. Okay, Ilya, can you can ask your question? Yes.
So
Ilya Shapirovsky.
Yes, your main result is formulated in. It is a.
Yes.
Can you hear me?
Yeah,
Hello?
we can hear you.
Yeah. So your main result is formulated in terms of like it gives you a criterion of existence of this measurable cardinal in terms of the fact that the logic of a certain space, there exists a space which logic is a certain logic is fixed out, right? So do you think we could expect that this can be reformulated, your criterion, in terms of validity of a certain model formula? So there exists say a normal extremely disconnected space validating a given fixed formula if and only for a measurable cardinal. Do you think we could expect this kind of result?
Yeah, in this case, you can, because this you can describe this logic with one formula, right? I mean, you just add one. I mean, this is a finitely axiomatizable logic, right? So you basically add one formula to it, right?
But it means that the logic of space contains this logic axiomatizes this formula, not necessarily equal.
Well, I mean, the theorem says that the logic is exactly the logic of the diamond, right? So it's exactly that formula, right? I mean, think about it this way: the L of this L is S4 plus 1 formula, right? So now this result says that existence of measurable cardinal tells you that this logic is exactly the logic of that normal ED space, right? So that means that tells you that that axiom that this logic is determined by, that's the axiom that describes the Z, right? Am I not understanding your question well?
Well, maybe this is the answer, but I still do not get it because I see that. Well, your condition is it seems to be stronger that the condition I'm asking about. It says that the logic is exactly the logic.
Exactly, yeah, exactly.
Yeah, but I mean that just a certain formula is valid.
So you're just asking about the validity.
Right, validity of just one identity of a single
just validity. Just validity, I don't know. I have to think about it. Just validity is weak, you know.
That wouldn't follow from this result, but maybe there's enough in the proof to get that. But our
that would be kind of modal expressibility of this condition of existence of measurable cardinals.
Yeah, exactly.
Yeah.
Okay, that would be
interesting. Yeah,
something interesting. I see Valentin Schechtman has a question. So please, Valentin.
Yes, my question is about another result that you mentioned before. That you mentioned the result that if you take a Stone-Check compactification of omega, then there is a certain logic that you can characterize it by this way.
Yes.
So do you know or expect anything about characterization of Stone-Check compactifications of arbitrary ordinals? Should they give you a family of extensions of S4.2 as well, or what can they be?
So Stone-Check of any Stone-Check of any ordinal. Let me think about that. No, it may not give you S4 because Stone-Check of a space is extremely disconnected if and only if the space itself is extremely disconnected. So if you start from an ordinal which is not extremely disconnected, then you will not get S4. You will not stay inside S42 anymore.
Oh yes.
And yes, it takes you out. But it's a very good question. I mean, that I don't know. The quick answer is I don't know, but it got my thinking going.
But it gives you compact Hausdorff anyway.
Yes, even more. It gives you. I would guess it also gives you Stone space. Gives you zero dimensional probably because ordinals are zero dimensional, and I think that Stone-Check preserves zero dimensionality. But S42 but this extremal disconnected is you're losing, and that could be bad news. I'm gonna think about that.
Okay, there is a question from Denis Savelyev in the chat. You can open it and read it. By the way, guys, you can write more in the chat because then your questions will be somehow not forgotten and preserved.
Yeah, let me, in order for me to get to the chat window, I need to minimize this thing. So just give me 1 second. Because I'm not.
Or Dennis can actually say something if you have.
Yeah, okay, so this thing is minimized, so I should be able to see the chat window now. Hold on.
You go downwards with your mouse until the very bottom, and it should somehow appear there. Or maybe to the very top or something.
Yeah, here it is. Oh, chat. Here it is. Yeah.
Mm-hmm.
So the question is, it seems that modifying the argument, it is possible to get an ED space with logical poset consisting of an anti-chain of any given finite size. Yeah, I think you can you, so Denise, can you hear me or not even, or should I type in or should I just speak?
You can speak. He definitely can hear you. He may not be able to say anything. That we don't know.
Okay. It's so the question is the following: that instead of the diamond in the middle, put as many points as you want, and then can you modify? The question is whether the construction can be modified so that we get that logic. And I agree that. Remember how I did only 2 copies when I did the construction? So if you want to do n, you just do n copies. Then the combinatoric is going to get a little harder, but I think that not too hard. So I agree that if you modify that, you can get any, I don't know what you call these configurations, but imagine that in the middle, instead of 2, you can have an arbitrary n.
Yeah.
Yeah, so that's a good point. I think that that's possible by simply taking bigger disjoint unions.
Mm-hmm.
Can I?
Yes.
So perhaps if the answer is yes for this question, then it might answer my question as well, because in this case we get what we get. Gregorchik plus confluence plus height of 3. Validity of this means validity of this in a phrase.
Yeah.
Give
Yes.
you not completeness with a certain logic, but just validity of this. Gregorchik plus height 3 plus confluence.
Yeah. Yes. Yes, that's.
So you
yeah,
just need a
exactly
formula definable class of frames, right, with which to do your construction, so to say, in a sense.
Yes. Yes.
Maybe that's even possible.
Well, I don't know whether it will be a positive formula. I don't, because I mean that what is that? Because I'm already Gregorchik is not a positive formula, right? But maybe you can rewrite it, right?
Yeah. Anyway, probably will not be able to solve that problem right now.
But I wrote down all this all these questions I wrote down, and I don't know whether I can tell you very much, but I'll definitely, if I have anything useful to say about these questions, I'll especially Valentin's question could be difficult, you know. So
sorry, I've got another question. I realize that I have another question.
okay.
So maybe it's just a guess. Maybe you can do better and without this measurable cardinal axiom for the intuitionistic logic of this over space.
That we thought about, and
Yes,
and we cannot do without measurable cardinal.
for intuitionistic as well.
Yeah, we cannot do without. Even in the intuitionistic case, it's equivalent.
I see. I see.
Okay. That's
Thank
nice.
you.
Because this result directly translates, because I mean this because of this Gregorchik thing and because of Bloch-Sakia, this will translate directly.
Okay.
Bloch-Sakia basically tells you that you have to use the same technique. I mean, there's no way around.
Okay, thank you, Guram.
Okay.
Thank
Are
you very
there
much.
any other questions?
Thank you.
Yeah.
I think I have a small question.
Yeah.
Can you
Please.
hear me? Yep, I think I'm here, but I
Yes,
think
so
nobody
done.
can see me, unfortunately, because they've removed me from the video chat.
Mhm.
So maybe some sort of stupid question. So we have a specific model here, which is the diamond. But what if we consider other, I don't know, finite structures, maybe more complicated?
That's a very good question.
So do you expect something bigger than the existence of one measurable cardinal, or should it be the same or something like that?
Yeah, so the quick answer is that I don't know, but there are some things that that we encountered that the more complicated you make your configuration, I mean, as long as it's a finite configuration, it's okay. But for example, one of the things that we encountered is already in depth 3, we encountered the logic which above Grzegorczyk, which is the logic of a scattered space, but of depth 3. But because of the difficulty of combinatorics, we cannot, because of already in depth 3, you can have, now I'm not assuming that you are above S42 anymore. I'm assuming that take any rooted frame of depth 3, and then you have difficult situation. Already back in the 70s, Kuznetsov proved that as soon as you are depth 3, there's continuum many of logics, right? So already these combinatorics could be very difficult. And so one thing that we couldn't determine, up to this day, it's an open problem, is that there's a specific space, a very simply described space that played an important role in topology back in the 60s and 70s. And there's a Polish name associated with it, that name is Nick. Do you remember that name? So there's this name of a Polish topologist that's escaping me right now, but so he worked with these spaces, and so there's a very simple space of Cantor-Bennigsen rank 3, and so you know that the logic of that space is above this Grzegorczyk of depth 3. But because of these difficult combinatorics, we were unable to tell exactly which finite configurations are interior images. And so what happens is that, and that's exactly when I said that I'm pessimistic about full characterization of these logics coming from scattered spaces, because already in depth 3, the combinatorics gets too difficult to handle some of the things. And so the basic idea is that the more complicated combinatorics you make, the harder some of the basic questions are to answer. So I guess that in general, Mrovka, yeah, thank you. Thank you, Valentin. Mrovka, yeah. Mrovka spaces, you know, so. I think that you have to play a very careful game about how difficult you want to make your configuration, because the combinatorics can get out of hand. And that's just, I don't think that I directly answered your question. I think that you can change your configuration, but you have to be careful how much complicated you make it. And so it's a fine line to walk, I think, you know.
Okay, yeah, I see it.
Okay. But already for this diamond, I mean, I wonder that already whether for this diamond, you can actually maybe restrict your class of normal spaces further down and then prove existence of some some large cardinals just by cutting down normal further down. So that I don't have any evidence that is going to be either yes or no, but clearly there seems to be some connection between topological completeness above S42 and existence of some axioms of set theory that are not provable in ZFC.
Yeah.
And I think that it would be good to learn more about that.
Okay. Yeah, definitely the remaining question about removing this normality condition is also quite an intriguing
That's also, and I think that you need a different technique for that.
Yeah. Right. Good. Yeah, thank you for this very interesting talk that had many.
Thank you all.
Many of our participants had connections with different parts of your of your talk, as well as set theoretic and as well as modal logic and topological. And don't forget that you promised to give us one more talk sometime later.
Yes, yes, I'm gonna keep my promise.
Okay, very good. Then with this, I think everyone can switch their own sound and do some.
Thank you. It was well, a pleasure.
Good, you can hear it. Yes. Yeah. Спасибо. And goodbye, everybody. Yeah.
Yes.
Mm-hmm.